Welcome, everyone. I believe in this room everybody will agree with me that the number one superpower of Erlang is fault tolerance. And fault tolerance is achieved by the means of this clicker is not working, and this one is not working either, sorry. Because because things happen behind my back that I didn't notice. Great. So it's built on the principles of isolation and supervision. Which means that if I forget about something like I have a dependency that may limit me one day with an HTTP response of 429, then it's typically not a big deal. My worker process will crash, but it's isolated from the rest of the processes, so they keep working, including the supervisor who will be able to handle the error by restarting my worker. And hopefully a few restarts later, my request will go through and we are back to business. Well, at least that's the theory. But what if these assumptions don't always hold? What if I would run into a bug that is persistent? I mean, it may have some particular preconditions to happen, so I cannot really catch it in CI, but in production, it hits me every time, and it's not going away. That's quite a scary thought. Or what if I have another bug that can somehow slip through the shared resources from one process to another, because processes do share a lot of things. They have monitors, links, ETS tables, they share CPU and memory limits, the file system. So there are plenty of possibilities for a bug to bring down such a big part of my system that it cannot recover on its own. These thoughts can make you feel very uneasy, even if your system is written in Erlang. Okay, but what if you have distributed your application for fault tolerance? Well, I'm afraid we are still not out of the danger zone here, because fault tolerance of a distributed system is still built upon the same principles. Only in this case, we have a whole host instead of a process, and we have Kubernetes or some autoscaler to restart my entire application instead of an Erlang supervisor. But just imagine, if you have a bug that has the blast radius, that it can knock down one of your nodes, and this bug occurs frequently and reliably enough that it will eventually hit all your instances in the cluster and can kill the entire cluster. That's a cluster killer bug. That's actually one of my worst nightmares as a developer, at least. Yeah, I'm Dániel Szoboszlay from Klarna Bank. And today I would like to talk to you one experience we had with one such cluster killer bug that happened about a year ago. And it took us down a very interesting, scary, but fascinating rabbit hole through the core of our tech stack. But before I really begin, I would like to... Okay, can I do this one? Oh, because somebody would like to come. Never mind. They would like to paint the landscape a little bit before I start. Thank you, this is perfect here. And talk a few words about Klarna and Kred. So Klarna was a company launched in 2005 as a buy now, pay later company. And at that time, it was powered by a single Erlang system called Kred. So time went by and Klarna grew quite successful. So now it became a unicorn and then a decacorn. Nowadays it's present in 20 markets, has 7,000 engineers and handles about 2 million purchases a day. And Kred grew with Klarna, but luckily I may say, we are no longer the only system in-house. That would be a bit too much responsibility, I think. But there are other systems as well. And we are working hard to make Kred focused on doing one thing and one thing only, but we are not quite there yet. So it's still a big monolith with a lot of responsibilities, which you will see in its architecture. So architecture-wise, Kred is a distributed system running on multiple nodes. And each node has an amnesia database, so our nodes are at once application and database nodes. But we don't use amnesia for replication. We use a custom protocol called KDB. And in our system, we have one dedicated leader node. That's where all the transactions happen. And then KDB will sync the updates to the rest of the nodes, the so-called followers. As I said, Kred has a lot of responsibilities, so it has a bunch of APIs as well. First of all, it has a use web server, that, yes, that's all, that the human users can use. And we have a REST API for other systems in Klarna to connect to us via synchronous requests. And since these interfaces are very read-heavy, they are served by the follower node, so they connect as read replicas themselves. But we also, and if they have to do sometimes a post request, which involves a transaction, then that transaction is done via an RPC on the leader. We also have Kafka in Klarna. It's used for sending messages to other systems, including to Kred, which don't need to be handled in a real-time fashion. You can batch them up. And all these consumers, Kafka consumers, who live in the leader because they will do a lot of transactions. Every message we consume will involve a transaction, so no reason to put them somewhere else and then do an RPC. But we also do so-called stream processing works, which means we consume messages from Kafka, do some processing, and then publish the result back to Kafka, not into our own database. And that is work that we can put on the followers to offload the leader a bit. That's what we would like to do in general, offload tasks from the leader. Okay, this architecture has some consequences on how do we operate Kred. To put it in a nutshell, our servers are unfortunately still pets and not cattle, which means that first of all we need a lot of memory because we have in-memory tables for Amnesia, and also we need a lot of disk cache for the operating system, so the level DB tables can be kept in memory as much as needed. This implies that we use relatively few large beefy instances instead of a swarm of small and cheap nodes. This also implies that since the nodes have 6 terabytes of data each in the database, it takes quite some time for them to boot up. They need to load a lot of data into memory. It takes minutes. And once they are done with that, they still have to sync the changes that happened while they were offline from the leader, which can be anything between a few seconds and hours, depending on how long the node was offline. And it also means that because we have so much data, that provisioning a new node, it's a lengthy process. It takes too much time. So unfortunately, we cannot do the nowadays trendy way of, oh, this cluster is misbehaving, let's just kill it and spawn up a new instance. It will not work. It takes too much time. Our preferred way of troubleshooting instead is that we go onto the host and try to figure out what's going there and fix it without hopefully restarting anything. And if fault tolerance was the #1 superpower of Erlang, I think, how to say it, this troubleshootability, being able to inspect the state and then make changes, it comes in as a close second, I think. I would like to divide this troubleshooting process into 3 phases in my mind. So first you have alerting. You need some system that will wake you up in the middle of the night if things go wrong. And this is not a superpower of Erlang. We are doing just quite well in this regard. We have a lot of libraries that can collect logs, metrics, whatever, and push them to other systems that are good at waking up people in the middle of the night instead. The real superpowers happen after this, because sometimes you don't get a very specific error or pointer out of the alerts. You just say, looks like you are using too much memory. And then you have to go there, dig down, and identify the actual root cause. And the first superpower here is you can actually have a shell access. If you are using Ribarcy or Relax, you will get it for free, basically, with the command line option for your boot script. But you can also use the plain Erlang rem shell command, either locally from the same machine where your server process is running, or even remotely if you don't have any firewalls blocking access. And once you're in, I guess everybody knows about Observer and uses it. Well, you normally can't use it on production machines because it's a graphical tool and you don't have those libraries there. But don't worry, you can get the same amount of information out from the shell, from the CLI. The first type of information everybody tends to be curious about is what progress is happening there, that is tracing. I don't like tracing that much. to be honest, because the raw API is a bit inconvenient to use. We have some wrappers like Redbug, but still, it's mostly not what is the most interesting for me. I typically find what is the current state of the system more important, because what if, for example, your system is not progressing at all, it's stuck in some deadlock. And then you have a lot of tools. You can go with sysget state to inspect the state of OTP compliant processes, gen servers, gen statums, whatever. You can do process info. And I would like to call your attention to this BT, which stands for backtrace. It's a shell built-in. That's the only one I would like to go into detail. It can give you very low-level information on what a process is doing. It looks something like this. It's a bit cryptic to read, I think. So I will try to help you decipher it. So the first line program counter blah, blah, blah says that this is the memory address of the operation this program is executing at the moment, which is somewhere inside gen do call. I can't make any use of the memory address information, to be honest. And then comes these lines with y0, y1, whatever. These are values that gen do call pushed on the stack. These are values that it will need in the future once the current operation it does finishes. And without looking at the disassembly of the module, it's not easy to figure out what these values mean, but sometimes you can make a guess. So this is a gen do call, so we are doing some call. We will need, obviously, a PID of the process where we send the message. We will need, obviously, some reference that we expect in the response and or in the down message if that goes down, and the timeout. And you can just spot these things in the stack because we have one PID, one reference, and one infinity atop there. But the purpose of those two empty lists, I don't know. Then we have the return address line that says, from now on, we see the stack of the previous function that was called in gen do call, gen server call in this case. Let me show you what you can make use of this in a minute. And the last thing that can be of interest is looking at actually the terms that you can back from looking at the state of the system. And I really like that in Erlang you get very good transparency of the terms. You can just pretty print everything on the shell and you will see what's inside. Almost everything. Some caveats are records, which by default don't show up with record syntax. You can help it in the shell with the rr and rp commands. We have resources that are tied to a node, like PIDs, monitors, ports, and it's not obvious to which node, but you can query that as well with Erlang node. And you have the first offenders, these are funds. Funds, anonymous functions, they can capture values from their environment. And those values are not visible when you print the fun, even though they are there. But you can use the Erlang fun info function to look into that and see what went actually inside of this fun. Okay, so what can we make use of all this information? We can use it to fix the problems. And when I started working with Erlang, fixing problems was the synonym of doing hot code upgrades, hot code loads. And at that time, it was a superpower to me on its own, because I didn't know about any other runtime system that would let you do that, any other language, maybe save for PHP, sort of. Nowadays, other runtimes, I think, caught up a little bit with Erlang in that term, but I also have some new tricks under my sleeve, like I learned how useful sys replace state is, which is meant for fixing or changing the state of a gen server or gen statum. But you can also use it to run arbitrary code within the process. So you can do things that are only possible from within the process, like placing monitors or creating ETS tables that are owned by the process, or changing process flags or whatnot. And this can be useful because code loading doesn't always solve the problems. If you are already deadlocked, then you probably have to go there and change the current state of the processes to recover. Or you can forge messages to unlock them. And that's where the backtrace comes very handy, because you can figure out values like, okay, this process is waiting for this reference to get back. And then you can forge a message for it. Anyway, fixing is too complex. I don't want to go into more details here because it depends on the specific scenario you have. Let's see how it is pulled together, how we use our framework of alerting, identifying, and okay, and fixing in a real-world situation. Yes, first step is alerting. This was an event, an incident, where the symptom was that memory started to grow across all the nodes. First on this light blue node, and then the dark blue followed suit about after half an hour. And this was clearly anomalous. So monitoring should trigger and wake you up that this is not good. It didn't happen, by the way, because we didn't have the threshold set fine. We were looking at a 5-minute average of the memory consumption, and these were too spiky. So the 5-minute average barely hit 50% memory utilization. What actually rang the bell was when this happened. The dark blue node ran out of memory and crashed, and usage went back to 0. Never mind. At least alerting worked. We got informed about the incident. And by the way, I'm sorry for the quality of this graph. I know it's hard to read, but I don't have anything better. This was the only screenshot I made at the time of the incident, and back then I wasn't expecting to give this talk. And by the time I realized I want better charts, the data was already thrown out because we don't have infinite retention time. That's the best I have. Sorry for that. Yeah. So then you go on and start to identify things. I told you that the shell access is all you need, but if you have better tooling, then it can be even better. We have better tooling. It's called System Monitor, which is open source. I highly recommend for anyone to use it. What it does is basically goes over all your processes every 2 seconds, finds the biggest ones, and reports information on them to a Postgres database. And from Postgres, you can use Grafana to throw this observer-like dashboard about your processes, which is even better than Observer because you can time travel. You can go back in time and see what happened in the past. And this is actually not real data from the time of the incident because, once again, I didn't make any screenshots, and when I realized I want some, the data was gone. You can time travel, but not indefinitely, just as long as you keep the data. But let's say in this example, the first process seems a candidate because it uses a lot of memory. It was even more obvious at the time of the real incident. So System Monitor lets you click through that process and then see the history, how much CPU memory it used, how its message queue went over the time. In this case, unfortunately, it wasn't very revealing. What happened instead is, now that I had a PID, I could go to Splunk and search for the logs. Logs typically reveal very easily what a process was doing in the past. And in the audit log, I found this entry, which tells me that this one was handling GET request to some YO space. So this is a YO's worker process. I even know who was the guy who initiated it. And this is an engineer from within Klarna. And know the parameters of this page. That's a curious one. Cut date is 1st of January 2001. Even if you don't know too much about the internals of Kred, you can guess what happened. This is a report page, and somebody said, oh, show me a report from the beginning of the time. Obviously, it takes a lot of memory. It will read up the entire database for you. And it has one more bad property. This report will take ages to compile. So what will a regular user do? Get bored and hit refresh. So now you have 2 processes doing the same thing. And then the second one will not complete either, so he will press refresh again and again. And here it is. This is a cluster killer bug, because this bug has the blast radius to bring down one node because it will run out of memory. And it is permanent enough because we have a very persistent user who pressed refresh 23 times in our case. And thanks to our good load balancer, it eventually hit all the nodes. So if you don't act quickly enough, it will just kill every single node in your cluster. We were lucky. We could act quickly by killing the processes, which was a very simple short-time fix. Long-term fix would be, of course, not allowing these kind of reports to be generated, requested. Yeah, so this is a cluster killer bug. I talked about it, we found it, hunt is over. I can give back to you about 25 minutes of your time, I guess. No, I'm just joking. This was actually a cluster killer bug, but I just want to put it as an illustration that sometimes very minor things can cause big issues. We had actually a much worse day than this good one. Let's see the story of that. The bad day started as any other day in the life of Kred. The only interesting thing was a scheduled maintenance of the Kafka cluster. But this is nothing to worry about. The users of Kafka won't notice the maintenance going on, and worst case, you have a Kafka outage, and then what happens? These are not real-time messages, they are badged, so we will just wait a little bit, and then once Kafka is back, we will catch up. Obviously, the maintenance went bad, and one of the nodes had to be killed with kill-9 style, and then Kafka really struggled finding a new leader for the partitions that were owned by this node. All in all, it affected only less than 5% of all the partitions in Klarna, but still it caused smaller or bigger issues in almost every system in the company. It should have caused a very little issue in Kred. Instead, it caused quite a big one. So the first symptom we had, and once again, I'm sorry for the graphs, this is the only one I took at the time of the incident, was memory going up. We went up by about 140 gigabytes over a 20-minute window, which is tolerable, but not nice. The second problem, which is already visible in the graph, you can see we have a green line that shows what the operating system reported via collectd. But we have also a yellow line, which is what Erlang reports about itself. And there's a big gap over the incident. We lost all our metrics from Erlang. What happened? This is very unusual. We were half blind during the incident. It's not the end of the story. You know, you have shell access, you can do anything. Well, turns out that shell access timed out. We couldn't get access to nodes. We were not just half blind, we were actually paralyzed, not able to do any of our regular troubleshooting processes. Okay. Then, after about 20 minutes, here, Kafka came back, and then Kred became super busy. Oh, by the way, we saw in the logs that it was still working over those 20 minutes. It was doing some actual work, just metrics were not showing up. And here it became very, very busy. It was doing a large peak of transactions, a large peak of memory, and actually we used up all 768 gigs we had, and the leader went down. That's bad, that's not what we want, but never mind, never mind. Kred was designed for this scenario. If the leader goes down, one of the followers will take over. It did, but it managed to do exactly 0 transactions. We don't have many logs from this period that would explain what happened, but what we have is there were a few transactions that had a timeout on them. And all of them said that they reached this timeout while doing a code server call. This is the point where they got stuck. And then the sixth symptom, okay, there is no sixth symptom, that was all. This day was already as bad as it got. So we realized that the Kred will not recover on its own. We had to kill the remaining nodes and start them from a clean state. And then it was over. But it still left us with a lot of question marks. What happened? How did it happen? Can we apply here our framework of troubleshooting, alerting, identifying, and fixing? Alerting worked. We got aware of the incident. Identifying, we were stuck. We couldn't dig down during the incident because we didn't have any shell access. We lost all the metrics. You can do 2 things in this scenario. First, you can try to reproduce in a more controlled test environment, like you can have a shell already open and hope it will not stop working. And the other thing is you can just guess about the root cause. And let me be clear here, guessing is fine. Sometimes you cannot do better than guessing. But if you have to do that, then always remember to validate as well. Validate that your guess root cause indeed explains all the symptoms you have experienced. And when you deploy a fix, validate that the fix indeed eliminates the issue. So can we do that? What was our first guess? Our first guess was around the slow memory growth. So this is probably due to Broad or the Kafka interface library. We are producing messages to Kafka, and if Kafka is down, then those messages can't go out. They are stored in a buffer for a while, and then Broad will keep retrying. But after a while, Broad will give up, as any good Erlang process would do. And then it crashes, and when it crashes, here comes an error log about a big crash log. The crash log contains the state of this Broad producer server, which state contains all the messages. So if you have a lot of messages there, then obviously this will be a huge report. So maybe that's why we saw that huge memory spike, that it crashed and then that took down the node. Let's see how this guess holds up against our evidence. Some back of the napkin calculation. Let's say we have 1 gigabyte worth of data in our buffers. Then we pretty print it. This is binary data, so each byte will become a decimal number separated by colons, so around 3.5 characters on average per byte. If it's an Erlang string, then each character takes 2 words to store, and each word on a 64-bit architecture is 8 bytes. If you multiply this together, you will see that it's 56 gigabytes if you want to pretty print the 1 gigabyte binary and keep it in memory as an Erlang string. Could be the reason, at least doesn't sound impossible. Although it would be very, very stupid from the OTP logger to keep the entire data pretty printed as a string in memory. But stupid bugs happen, so maybe. Okay, one further proof that we found was this incident report from the Broad repository, which is a long one, but basically it says somebody has experienced the exact same issue that we did. And they had a fix, which was, let's change format status. So when the process crashes, we remove this buffer where the messages are. And then this eliminated the issue for them. Awesome. Can we validate whether this hypothesis explains all our symptoms? First, memory growth, yes, that's where we started from. The big spike at the end, we knew that, sorry, memory growth, the slow memory growth could be just the messages piling up in the buffer, and at the end, we try to pretty print them and then go down. We know that this bug never happened before, but now it hit all the nodes. What could happen? If you remember the architecture diagram, the Kred leader doesn't produce anything to Kafka, so it should be immune to issues with the Broad producer. Well, except it did. So we had one particular use case for producing to Broad, and this was the aforementioned system monitor, which at the time sent its data to Kafka, and from Kafka it went into Postgres. So this was one particular partition where every node was producing. And it sounds plausible that before, when there were Kafka issues, that single partition was not affected, so we didn't notice. Now we were unlucky. It hit all the nodes. Okay, sounds like a theory. What about no metrics, no shell access, and the paralyzed leader after the failover? Unfortunately, we cannot explain with this theory how these things happened. And then we tried to reproduce the issue, and it turned out that the fix in the Broad PR was proposed indeed fixed the issue. But we had a second idea. Let's put some limits on the pretty printer so it won't go infinitely deep into terms, and that should have fixed as well, but it did not. That fix didn't work. So something is fishy about this explanation. It's not what it's not enough to explain our problem. Back to the drawing board. Let's come up with a second guess. And our second guess was about the metrics. What happened to the metrics? Why did we lose them? And the path of the metrics in the Kred is that they are kept in a Folsom, then go to Folsomite, which converts them to graphite's format, and then they end up in graphite. We know graphite was working. It received the collect metrics from the operating system. So the problem should be somewhere in Folsomite. ForSum did not crash. There were no logs about it. So it makes sense that it was blocked. It was trying to work, but it could not. What is ForSum doing? If you read the code, you will find it's a gen server doing a periodic, waking up periodically and doing this get stats thing, which, among other things, will do ForSum VM metrics to collect memory and information and other VM statistics. What if those things blocked? What if there was a scheduler lookup that prevented us from getting this information? What is a scheduler lookup, you may ask? So let's quickly talk about schedulers. So scheduler in Erlang is a thread in the VM that executes your Erlang code. Normally we have as many of those, as many cores you have, and they are meant to be very responsive. They should not get blocked running one process, but switch often, so every process gets its fair share of the CPU. This assumption is both heavily worked to us, so the OTP code is written in a way to provide you this guarantee, and it also relies on it. So, for example, if you want to get information like total memory usage, then every scheduler has information on its own memory allocations. And if you want to collect a global view, then have to query all the schedulers and sum up the values. And you cannot query a scheduler while it's doing something else because it may concurrently do memory allocation. So that would be a bad thing. There are locks in place. So if one of the schedulers would keep executing for a very long time in an Erlang process, then it could lead to trouble. And when you think about what does it take to make things preemptive, first, you can schedule out an Erlang code between two operations in the bytecode. But if you think about it, even the individual operations, the lowest level things that the Beam VM does, need to be preemptive if they are not constant time. And most things are not constant time. Even think about it, just integers. They can be arbitrarily big, so even just multiplication or addition, the basic mathematical operations can take arbitrarily long. So everything should be basically preemptible in the Beam VM. And the OTP developers did a very good job in guaranteeing this. It was not always like this. So 5 years back or so, we had some notorious operators like plus and minus, I think, that tend to block for a long time if the arguments are big. But nowadays everything is nice and preemptive and fast. But maybe they missed something. It wouldn't be unheard of. And the problem with these scheduler lookups is that they start spreading in your system. So first we have one scheduler where one process gets slow. Then it will not release the CPU, or the processes in this scheduler gets blocked. And the system gets, oh my God, it gets worse. So if you do, for example, an Erlang memory core here that would need access to that scheduler, it will block that process. And if some other process would do a process info on a block process or do a gen statem call to another process that blocks because you need an answer, then those get blocked as well. So it starts spreading, and soon your system will come to a halt. It's a big problem. So, new theory. How does it check out? We started with no metrics. Yes, obviously we can explain it. Memory growth. If there's a roadblock and more processes start to run to it, then it can cause memory growth. We don't know about parallelized leader and no shell access. Let's try to verify whether this can happen. Let's test for scheduler lookups. That's something I can't do anymore from the Erlang shell because I don't know a way for deadlocking a scheduler process. So let's instead go down one step below and use the GDB debugger, which is uncharted territory for me, by the way. But let me try to do my best. And by the way, if you want to do this, then don't forget to install the debug info packages for Erlang. Otherwise, you will not get nice function names and variable names, just hexadecimal numbers everywhere. So first thing is you tell GDB that you want these things target async and non-stop. Otherwise, it would just stop the entire process you are debugging. That's not what we want. We want it to be remain responsive, except for one single scheduler. Then we start an Erlang node. As it's OSP, then we can use it in the debugger to attach. And once you do that, it will immediately suspend all the threads and print you a lot of info. This is not what we want. We want to continue everything and then get a more easier to overview look of what processes are, what threads are there. And there are a large number of them, even on a 4-core machine like my laptop. But they are nicely labeled, so I can pick one of the schedulers. So let's call it over, and I can say, let's interrupt thread 9. No, the scheduler 5 is stopped. Back to Erlang shell, it still operates. The rest of the schedulers are fine. But if I try to connect with the remote shell from another machine, that is blocked. Okay, this holds the scheduler lookup. I don't know about what exact mechanism, but explains this symptom. What about loading a module? That works, because I was expecting that code load to block on loading a module that I saw in the timeout logs. It works. Okay, but maybe the problem is that this scheduler, it's doing a syscall, so it's basically just waiting for something to wake it up. It's not busy. Let's try what happens if it's busy. So we write a loop function that will just do something stupid, and then we want to spawn it and break its scheduler. But how do we know which scheduler it's running on? Well, here comes the Erlang process scheduler, which is a neat tool. You can pin a process to an actual scheduler. And then I know it will be on scheduler 5. Use it for debugging, don't use it in production, of course. Here I have to continue this process for momentarily and then interrupt again. And now I see that it's in some, what's the name, process main. This is doing something. I break the process in the middle of doing some Erlang code. Back to the shell, try to load something, blocks. This is proven. So, get back to here, validation. We have ticked the 2 remaining checkbox, and I have just a few minutes left to tell you how to find the actual runaway BIF built in, the hunt itself. So we knew from the first hypothesis that this has to be something related to the broad process crashing. So let's focus on that. My idea was that I will start a load test, block access to Kafka. This is how we reproduce the event in a test environment. Then wait a little bit, stop the load, and at that point, Kred should be idle, except one scheduler, which should be busy spinning in some function that logged up. Then I can attach GDB and look which one is that and what it's doing. And it worked. I got, luckily, one working scheduler, and the backtrace showed me that it was inside some function called sizeObjectS in ERTS send message in abifbank2. This was doing a message send. That makes sense. Sending message from one process to another is usually very fast, so maybe OTP guys forgot to make it preemptive. But at the same time, it's not constant time, because you have to copy the actual message to the recipient's heap. So it's proportional to the size of the message. This is the code where I broke it. Maybe it's not very visible, but this is the actual line where I interrupted the scheduler. If you spend a few minutes familiarizing yourself with the code, this sizeObjectX will count the amount of memory needed to hold a term and all of its subterms. It will be stored in this sum variable, and we happen to break it in a phase when it was looking at an anonymous function and was pushing all the free variables inside the anonymous function onto a stack of objects or terms, subterms to measure. GDB can even let you query the value of some variables like sum. And it gives back to you 90 billion something. That's not correct. This means that it already counted 90 billion words, which is about 720 gigabytes worth of data. This message will be bigger than 700 gigabytes. How could it be? Especially since my expectation is that the crash now happened in the beginning of the incident, when the whole node didn't have more than 150 gigabytes of memory allocated. And then it took 20 minutes for doing the message send. And then when the message send went through and I actually tried to allocate this lot of memory, then the memory spike came and we crashed. So how could it be? It would be very interesting to see what is this term. And I don't want to do this from the debugger because I don't know how to decode those Erlang terms. Let's try to go back to the Erlang shell and do it from there. Then I have to reproduce the problem in a way that it doesn't crash on me immediately. So I just took a sample program from Broad and modified it a little bit just by adding some config that says, let's have the retry time to 1 hour so it won't immediately kill me. Then I produce a message this way, block access to Kafka, produce more messages so they will be in the buffer, and then query this suspicious term with sysGetState, which of course blew up because sysGetState would send the state from the broad producer process to the share process, which is a message send, which of course takes a lot of time. And then, in my case, after sending 30 messages, wanted to allocate 2.7 terabytes of memory, which my laptop didn't have. And I didn't understand how, because before the problem, the whole Beam VM only used 22 megabytes. That's crazy. Okay, never mind. I tried with 10 messages, and then I got it back. This is the state. It's not very appealing, I'm afraid. Nothing suspicious here. We have a state record outside. Inside this, we have a buff record in the buffer field, which holds one request in an on-wire field. This is what we already sent to Kafka, but didn't get an acknowledgement back. And 9 requests in a buffer. Nothing strange here. Where could all that data hide? Well, I don't know furthermore because Broad has this tendency of putting everything into anonymous functions, so I don't know whether this request is about sending 2 bytes or 2 gigabytes of message. But never mind, we have this fun info, so we can look into this thing. This is the environment. These are the values that are captured by this fun inside the request. You spot something strange? There's an entire state record in it. So inside the state, we have an anonymous function inside which we have a state. It doesn't sound correct. This is the source of the bug. This causes the explosion of the term, but how? To understand this, we need to very, very quickly look into the this function and the layout of Erlang terms. So the problem here is that when I construct the function, I want to use state hashmark state.partition, and I guess the expectation was that only this single field of the state record will be captured by the fun, but instead it captured the entire state record. So terms in memory. If you look at, for example, a tuple, which is a so-called boxed term, we have this sample of T1 is foo 42, an inner nested tuple, and false. That will be laid out like this. First, we have a header for the for tuple. Then these are immediate values; they fit in the word foo 42, and we have now a pointer to the inner tuple up here, and then the atom false. If I want to update this term with set element 4, T1 to true, then I get a copy of the tuple, which still points to the very same inner tuple because this one wasn't updated. Only the last field gets updated. So basically, these tuples form a directed acyclic graph. I can represent the state record like this. We have the initial state, which is empty, which has a buffer inside, a buffer record, B0, which has 2 empty lists, an on-wire and the messages and the buffer of messages. When I create the first request, that captures inside this one the S0 state. I want to put it into a buffer, so I create a copy of B0. This will be B1 that points to this request in the on-wire list. And I have to put it in this new buffer into the new state, so I copy S0 into S1. It's already a bit bad because you see that this is actually garbage, but we cannot get rid of it. It gets worse when I create a second record, which will hold a copy of the entire S1 state, and it goes into a copy of the B1, which is B2. But remember, the on-wire part is the same, so this will just be a pointer to the existing R1 request. R2 goes into the buffer here. And when I create a copy of S1, that will contain B2. And this is the problem. And not just because of the garbage, but because from S2 down to S0, now I have two distinct passes. This one and this one. This means when I copy the term, that's a very dumb algorithm. It's a depth-first traversal of the graph, and whenever it encounters a term, it will copy it. If it encounters S0 two times, then I will have two copies of S0 on the recipient's heap. And that caused the explosion. If I would have more requests, then there will be even more passes. It exponentially blows up. And this bug is actually the root of everything, and I run out of time, which I'm very sorry for. But it was this easy to fix. You just have to parse this partition field out from the state record and only inject partition into this, into the fun. Then it will not blow up on copying. Then it will not take down your node with an out of memory, and it will also not cause scheduler lookups that explain all the other symptoms we have. So we can put a check mark to all of the boxes. Yes, basically that's how far I got. I'm sorry for overrunning my time. Thank you for your attention.